Okay, we're so back. I realised the audio in that first video was a little bit, I don't know, strange. It's very loud. So I've tried to fix that. Hopefully this is a bit better. This is the second video in this little mini 3-part series. It's on robust control. The feedback linearization will be used, which is why I did that first. And I'm just going to do one example. It's going to be a second order example because the method that I will be using effectively reduces the system order down to a first order system anyway. And that's, you can apply it to any nth order system. So I'm going to do second order for this one. Let's first understand the assumptions that we're going to have to make for this controller. These are that there is a system with unknown parameters that are bounded, and we can design a robust controller to account for the worst case scenario to counteract these unknown but bounded parameters. So if this is our system, let's first define the bounds. So what I'm going to say is that the absolute value of m is less than big M, and then same for C, and finally the same for K. So all this means is that M is smaller than plus or minus big M. Well, it's always in between plus or minus big M. So this is basically our bound for M and C and K. To start the controller design, the first thing to do is to reduce the system order, and we can do this with a so-called sliding variable defined as S. For a second order system, this is defined as E dot plus, which is our error dynamics, and I'll define them in a second, plus lambda E. And just to make it clear what E is, I'm going to just do this on the same line, I think. E is the error in our system, so let's look at our system state X. The error is going to be the measured system state minus a desired value, or in this case, for the sake of the example, a desired trajectory, so something that changes with time. And that is important because ultimately we're going to be taking the first or maybe even second derivative of E, and we're going to have x double dot minus xd double dot, but if xd is constant, xd dot and xd double dot are both 0, and it sort of can cancel out quite nicely, to be fair, but I think it's important to leave it in just to show you a sort of more of a general method to solving this sort of problem. Right, so what we want to do is make a controller that can basically have a hard limit using the bounds of M, C, and K, and basically use that to cancel them out. And I'll show you the method for doing this. What we do is we already defined our sliding variable S, and what we can do is we want to take the first derivative of S dot. If we look at this, it's going to be E double dot plus lambda E dot. Cool. Question is, what is E double dot? Well, we know what E is, so we can easily get E double dot. So I'm going to try and keep everything in so I don't lose track. S dot equals E double dot, which is going to be X double dot minus X D double dot, and let's not forget the lambda, so plus lambda E dot. Cool. That's S double dot. Well, we've just expanded out what E double dot is. We'll leave E dot for now, and you'll see why. We can basically just cancel it out. It should be noted that in reality, if we have a system with a sensor to measure our state X, and we know our desired input XD, E is known to us. We need to understand that first. We do know the error in the system. Otherwise, we would not be able to go anywhere with this. So this is cool, and you might notice already that we can actually expand this out a bit further. because we do have a system which can be put in terms of x double dot. Now, the way I like to approach these systems, just to make life a bit easier, is keep the m x double dot as m x double dot. Don't divide by m and cause it to become quite confusing. So I'm actually going to have to define here ms dot equals, remember now to times everything by m, m x double dot, which is great because we have that, m, let's not forget that, xd double dot plus m lambda e dot. Cool. So now let's quickly rearrange for mx double dot. This is dead easy. We have the system. We can just subtract c x dot and k x to this side, and we will get minus c x dot plus, minus kx plus u. Now remember that u is our controller. Well, it's a control input that we design, and the way to design it for robust control is to use feedback linearization. However, you will maybe remember that feedback linearization only works if we exactly know the parameters for the system, and we don't exactly know the parameters for the system. So we need to define a slightly different controller, and I'm going to call it u hat, and it's basically a feedback linearization controller, but we just need to take a guess at m, c, and k. So instead of m, c, and k, it's m hat, c hat, and k hat. So how would we design a feedback linearization controller for this? Well, remember, if we want mx double dot, if we want those dynamics to go to 0, the first thing we need to do is we need to add, so it's just going to be positive. Remember, not c, c hat, I guess it's c, and x dot, like so, and then add k hat, we don't know k, but k hat is a little guess, x, and now we need to have another look at our system. Note, when we put mx double dot into here, we're going to have mxd double dot plus m lambda e dot, and we can actually try and get rid of those dynamics as well with our controller. So what we need to do is we're going to need to add m hat, x d double dot, and then subtract m hat lambda e dot. Hopefully you see why we do this, because we have these two terms here, mx d double dot plus m lambda e dot, and when we substitute mx double dot into this mx double dot, these will be left over. So we need to we can design our controller u to help out with us later and try and cancel out those dynamics. This is fine. This controller would give us closed loop dynamics equal to 0, but actually, if you remember from feedback linearization, we want to add some other term, and I've called it v in the previous lesson, but I'm just going to jump straight into defining it here. That considers some controller gains that we can basically change and adjust how quickly we want the system to stabilize and this sort of thing. For a second order system, we can treat it as a PD-like controller, so it's just going to be k0 times e dot. Actually, what I'm going to do is, this is probably a bit of a learning experience for me as well, is I'm going to leave that out. We're going to completely leave adding any extra term and see where it gets us, and then see what we could add to the controller to make those changes. So I'm actually going to leave the controller as this for now, substitute it in and see where it gets us. So we're going to have mx double dot is equal to, let me just type that out, is equal to, let's substitute these things in, I'm going to try and group these c terms, minus c x dot plus c hat x dot minus kx plus k hat x. So that's just grouping the c and the k terms from this controller. And let's not forget we still have m hat xd double dot minus m hat lambda e dot. Cool. So what I'm going to do here is I'm going to try and make this look a little bit neater. I'm going to do this by defining an error in our basically our guesses at C, M, and K. To do this, I'm going to define m tilde as m minus our guess, which was hat, m hat, and then I'm just going to copy this because it's going to be basically typing out the same thing 3 times. So it's going to be C tilde is going to be C minus C hat, and K tilde is going to be K minus K hat. Cool. So we can already group some terms in MX double dot here. Let me do this. So it's going to be mx double dot is equal to, you'll notice if c hat is c minus k hat, but actually we have minus c plus k hat, it's just going to be minus c tilde, like this. And then x dot, they're both in terms of x dot, exactly the same for k. It's going to be, if it's minus k plus k hat, and this is how we've defined it, it's going to be minus k tilde. And actually, how you define it is really up to you. It's an error, so it's a difference between these things. I could have, and I probably should have, defined these as m hat minus m and c hat minus c, and then it would be positive c tilde here and positive k tilde, but doesn't really matter. Let's just not forget those signs, otherwise we might get a bit lost later down the line. So that's good. We'll notice actually we don't have the any m term in this side of the equation. It's only on the other side, so we'll leave this as is for now, so just hat m. But what I can do, they're both m hat, so I'm just going to do m hat once, and it's going to be xd, positive xd double dot, that's that one, minus lambda e dot, like that. Cool. This is looking a little bit nicer. Now let's substitute this in to ms dot, and you'll notice actually that m will be reintroduced and we will be able to generate an m tilde because we're going to have some real values of m. So let's do that here. S dot is equal to, substituting mx double dot as this, minus, actually my philosophy is never type it all out if I can just copy and paste, like that. So that's obviously our mx double dot, and now let's just add our m. So they're both in terms of m, these two terms here, so we're going to just do this, and minus, oh, is this the wrong way around? It is. What I'm going to do then is I'm just going to switch this to minus m, and then keep this as is. I think that's fine, yeah, that's okay. Cool. So now we have m hat and m, and it's plus m hat minus m, so again it's going to have to be minus m tilde, and both are in terms of xd double dot minus lambda e dot. So I'm going to literally just copy this, do that again, and now this all becomes minus m tilde times xd double dot minus lambda E dot. Cool. This is cool. This is nice, and we can keep on going from here. What we want to do to basically figure out what we might need to do to add to the controller, right, to make the system to turn this into a proper robust controller, is we need to basically find a valid Lyapunov function and see if we can try and make it stable. And we'll see we need to make some changes to this controller to make it stable. So a valid Lyapunov function that I would recommend using will be v is equal to m not exactly 1 over 2 ms squared. This is all we're going to need for now, and I haven't done a lesson on Lyapunov stability theory, but hopefully this is something it comes up all the time, so maybe in the future I'll do one. But what we do is we take the first derivative of v, and in this case that's going to be m s dot s. If you were to do this, you would probably write it as m s s dot, but I like to group m and s dot because we'll notice that we already have m s dot, and we're going to have to substitute some dynamics here. So let's do exactly that. V dot is equal to ms dot, which we already have here. Again, I'm not going to copy it. I'm not going to type it all out. If I can just copy it. So all of this, and this is all multiplied by s. So I'm just going to put some brackets around that and make that equal to s. So this is fine, but we can't really do much with this. C tilde, K tilde, and M tilde are errors between the real states which we don't know, they're unknown, and a guess that we took, which is all fine and dandy, but we can't actually plug anything in to get this controller to do what we want. So we know what we must do. If we want v dot equals 0, for example, which is how I'm going to go from now on, and I'll add something later to make it equal to some controller gain. If we want it equal to 0, we know we need to add something to the controller u, or in this case u hat, to cancel out basically c tilde, k tilde, and m tilde. And what this will look like is a so-called, it's called a sine function. It's a discontinuous function that is defined as sine of a negative number is -1, sine of 0 is 0, and sine of 1, a positive number is 1. So, and it will become clear why that's handy. The way we can do this is literally just add 3 sine terms to our controller u. So I'm going to come back up here. It's going to be minus, and I'm going to, how could I do this? I think I'm just going to have to call them k. No, I'm going to call them a0, sine, which is just sgn, s, minus a1 sgn s, remember s is our sliding surface, sliding variable, a2 sgn s, and then if we were to follow through, I'm not going to do it all now, if we were to follow all of our dynamics all the way to the end, these terms would just basically be preserved here, because nothing else will be messing with them. And this is where it gets very interesting. Remember, this is all multiplied by s, and sine s times s is just, actually I'll write this here, sgn s times s, or s I guess, is equal to the absolute value of s. And you can do this, you can figure out why that would be, but this is the case. It's pretty simple. Sine function is pretty easy to understand. So in this case, it's going to be a0 times this absolute value of s, a1 times the absolute value of s, and a2 times this absolute value of s. Now, all we need to do is make it so a0, a1, and a2 can cancel out these dynamics, minus c tilde x dot minus k tilde x minus m tilde x d double dot minus lambda e dot. And it's quite simple to do that because we have an upper bound or a lower bound or whatever it is. We have a bound. So with this bound we can say, right, if a0 was that bound and it was just times this absolute value of s, remember these are also just times s, we can say that it's going to cancel it fully out because this value, a0, is going to be, is defined to be larger than c, for example. So what we're going to say is, a0 is equal to, now remember, let's keep these dynamics x dot, and I'm going to say it's, because remember x is the state, we can control this, it's something we know, or not control it, it's something we know. So I'm going to do a0 as big C, like this. I mean, it really doesn't matter how you define these, it's up to you. A1 is equal to the dynamics for k are just x, so it's going to be big Kx, and A2 it's going to be big M, and the dynamics for M are slightly more complicated but not crazy. XD double dot minus lambda E dot. Right, so that will ultimately give us this, where sine s just becomes the absolute value of s, no longer multiplied by s, and s is just added to these, is just multiplied by these terms as well, so there's an s there, there's an s there, and there's going to have to be an s there as well. Now, as we've defined a0 as cx dot, a1 as kx, and a2 as m xd double dot minus lambda e dot, if we were to substitute these in, we know that the c, k, and m terms are all just going to be cancelled out by this upper bound of big M, big C, and big K, which would be handy. It's basically going to give us, I'm not going to do it all painstakingly, but it's going to give us v dot equals 0, which is okay. I don't mind v dot equals 0. It's stable, but it's not asymptotically stable, and we have no control over that now because we have no controller gains left in our system. So like I said, I was going to leave it out and come back to it later, and there is a reason why I left it out, and it's because it wasn't exactly E and it was actually in terms of S. But what I can do is I can go back. If I wanted there to be a leftover term here, all of this just cancels down to 0. We just need to make sure our controller, U or U hat, also has a term that lets us control the system. We can do as many terms as we like, but I'm just going to do one because I'm lazy, and we're going to call it K0S in the controller. And if in here there was K0S minus K0S multiplied by S, that would leave us with V dot, I want a big V, is equal to minus K0S squared. This is probably a better method to design this controller. Add a little controllable gain in there that we can mess with later. What this lets us do is we can basically set K0 ourselves. You know, this is something we have full control over, and then we can make it positive, which makes V not just equal to 0, it makes it negative definite, and that allows us to say, sorry, V dot. This allows us to say that the system is AS, asymptotically stable, which means it will get to 0 error dynamics in finite time. So that's it. I mean, that's it for robust control. a lot more complicated than feedback linearization for sure. It does use feedback linearization. I hope this wasn't too confusing. I realised my methods are a little bit more, they're in my head and it's sort of harder to explain out loud. But this is the general form of doing it with a second order system. You always define a sliding surface, a sliding variable to reduce the system order down to 1, which is why I haven't done that first order system as an example. But by all means, give it a go yourself. All that's going to be is your aerodynamics are just going to be E rather than E dot plus lambda E, and it will make life a lot easier. So you can give that a go. The reason why this is such a powerful technique is if you had, you're very likely to have a system where you might actually know all the parameters, like the mass. You can measure the mass. You might know dampening. This is something you may well know. But then actually, if it's a real system out working in the real world, you might have a disturbance that you don't know. So if it's like an underwater vehicle and you have a current that you don't know, you're going to have to include that in the dynamics as some sort of external disturbance. But what you can probably almost always say with physical things like underwater currents is there is going to be a bound. And that bound you can use on a robust controller, and it means that you can ensure that your system will remain stable whilst manoeuvring underwater, even when there's this unknown underwater current, which is very handy. But it should be noted that this system accounts for the worst case scenario. So it's maybe not the most controller friendly. Your controller is going to be doing a lot more work. Your control gains are going to be a lot higher. So this is a consideration, and there are methods to account for this. There's other control strategies you could use, but fundamentally this is at its core quite a simple, robust controller, and it is very powerful in real systems. There is a note on chattering I thought I should probably mention, and that is basically because we have this sine function, a discontinuous sine function. Imagine we had our sliding variable. Let's get little Tux paint up and I can show you. I can draw something to make it more clear. If we had, let me make something new. In the phase plane, if we had our system, and this is our sliding surface, this is S, and we want to slide our system towards this at all times, and we do this with these robust terms, the sine terms. Imagine this is a vector towards sliding surface, but the vector of our disturbance might look like this, but the dot product of these vectors is gonna, it's still gonna be something like this. It's still gonna always head towards the sliding surface. But what happens is when you get very close to the sliding surface, you're gonna imagine this sliding surface. Your system will come in like this, slide to it, and now suddenly is over the other side of the sliding surface, and the sine function means that the controller gain switches, and it's very high gain usually, switches very suddenly, instantaneously, to push the other way, and you're going to get pushed over the line the other way, but now it switches again, and again, and again, and again, and so on. And this is called chattering. It is not ideal for real systems, because a lot of the time our controller will be some sort of input to a thruster, or a motor, or anything. And chattering is not good, because it might mean that the actual physical hardware of our system is going to struggle a lot to deal with it, to deal with the constant high gain switching, and it could also add vibrations and unknown dynamics, harmonics and all sorts could be introduced to our system, and the controller could completely fall apart. There is means to counteract this, and all they include basically is by not using the sine function and using continuous functions. So sine function, it looks like this. This is 1 and this is -1. But what we can do is a saturation. Instead of sine function, we use saturation, and it looks like this. So between these limits, if this is minus 1 and this is 1, we have some sort of slope up, and what that means is there's a continuous function between these two 1 and minus 1, and all we do to implement this is we take our sliding surface and we just have to introduce a boundary layer. So if this is our sliding surface, we can say, okay, within this boundary layer, it's not very straight, within this boundary layer use saturation. So it's really, really high gain, and then when it gets here, it slowly goes to the surface. And it is going to chatter, but a lot less. And this is a lot more valid for real systems. But this is really important later in control, so I thought I should mention it in this lesson. There is a lot of things you can do to counteract chattering, and very smart people have came up with various methods that work reasonably well to counteract that. But yeah, ultimately this is it for robust. It's not too bad. It's reasonably simple if you understand the assumptions and the unknown parameters and the fact that they're bounded and why they need to be bounded for us to actually be able to cancel them out at the end. So that's all. The next lesson will be adaptive control, will be the last one. I will tell you all about that next time.